Let's discuss question number 40 from test 8. This is from theory of machines. So what is given? A vibrating system is shown in the figure. The flexural rigidity of the light cantilever beam is EI, the frequency of the small cantilever. So you have a cantilever beam which is supporting a spring and a mass at its end. Okay, so here you have a cantilever beam. So this has a flexural rigidity EI. That means a beam, basically it's massless beam, but only thing is it has some elasticity. Okay, so now this system, if I just look at the force balance, what will I get is the force mg is acting throughout the springs. This entire spring supports mg, and that adds, the entire force adds here mg. So the force wise, the same force is acting on the spring as well as on the cantilever. Okay, so now see, basic idea is I want to replace entire system with one spring mass system. That's my idea. Okay, so how do I replace now? So let's first see, let's compute the total deflection here. The force that is acting on the cantilever is mg through the spring, that is transmitted through the spring is mg. Now because of this, the deflection of the beam is delta b, and that is given for a cantilever when a force p, a load p is acting at the end. The deflection is PL³ by 3EI. This comes from a derivation in deflection of beams, SOM. Okay, so we'll take this. The load p is acting at the end, which is mg. So mg L³ by 3EI is the deflection of only deflection at the tip. Now how much does the spring expands because of the force mg? So now the spring, because of the force mg, will expand by p by k. P is mg by k. The same force is basically bond is, I can say that both are in series because the same force is getting transmitted. So the total deflection at the mass end will be deflection of the beam tip plus deflection of the spring. So that is nothing but mg L³ by 3EI plus mg by k, that is total deflection of the mass. Now if I happen to replace this entire system by this also should give me the same deflection, right? So the deflection of this will be mg k equivalent into delta of mass. Now if this deflection and this deflection are equal, then I can say that this entire system has a equivalent stiffness k equivalent. So let's calculate k equivalent. So k equivalent by m is g by delta mass, and g by delta mass, so let's write this. So g by, so delta mass would be m, so I'm just writing delta mass here. So mg L³ by 3EI plus mg by k. So g's, if I cancel the g's, so what I get is 1 by ml³ by m 3EI by k. So this is what is k equivalent by m. The natural frequency is root k equivalent by m. So it is root of this entire thing, 1 by your m, so ml³ by 3EI plus m by k. So if I happen to just simplify, I'll get 3EIk in the numerator by m k L³ plus 3EI. So that's what I get. Okay, k L³ plus 3. So this is just the natural frequency. The basic idea is I just want to find the equivalent stiffness, and that's what I have used the deflections. I've compared the deflections in the actual case, where in the actual beam plus spring case, what is the deflection, that I'm just comparing with this. I'm just replacing the entire system with this equivalent stiffness and mass, equivalent spring mass system, such that the deflections are same. Okay, so that is the idea, and therefore the option for this is A. Thank you.